Hello everyone. I am Xinhua Lu from Sun Yat-sen University. Today I am going to present our work, FA, Forced Prompt Learning of Vision Language Models for Out-of-Distribution Detection in ICCV2025. Recently, benefiting from the powerful cross-modal understanding and remarkable generalization capability of large pre-trained vision language models such as CLIP, few-shot OD detection has been significantly enhanced. Most of the existing methods improve OD detection by leveraging OD-related knowledge. However, relying on external auxiliary datasets requires substantial computational resources as well as labor costs. Then, OD data extracted from ID data are difficult to match the infinite real-world outliers encountered in practice. Rather than focusing on the intricate OD-related knowledge, our FA aims to fully exploit the ID knowledge and improve OD detection. Moving forward, our contributions are as follows. Firstly, we propose a simple yet effective framework, which fully exploits the ID knowledge to improve OD detection without focusing on intricate OD-related knowledge. Then, we present a forced prompt learning strategy to exploit richer knowledge beyond the textual semantics of class labels. Furthermore, we evaluate our method on diverse OD benchmarks, showing that our model consistently outperforms current SOTA methods. Here are the overall framework of FA. Our framework includes the learnable forced prompt and the frozen original prompt, both of which are initialized identically by a manual template, a photo of a class name. The learnable forced prompt treats the frozen original prompt as a reference, forcing its text features to become more salient compared to those generated by the original prompt. The richer description of ID classes learned by FA can ultimately improve OD detection. During training, we introduce a simple yet effective training strategy using the forced cross-entropy, FCE, loss based on the forced prompt and the original prompt. In the formula, S represents the cosine similarity between the image features and the text features. Based on the FCE loss, the forced prompt is forced to uncover richer discriminative information of ID classes, so that the text features of the forced prompt achieve a higher cosine similarity with the image features compared to those of the original prompt. To encourage the forced prompt to capture more comprehensive and nuanced descriptions of the ID classes, we introduce a forced coefficient k, leading to the final form of the FCE loss. Notably, when k equals 0, no original prompt is used, and the model operates equivalently to COOP. During inference for the downstream classification task, we adopt the same strategy as CLIP, depending solely on the forced prompt. For the OD detection task, our method can be flexibly combined with different score functions, such as the MCM score and the GLMCM score. Benefiting from this information specific to the ID classes, the cosine similarity between the image features of an OD image and the text features of both prompts may exhibit less distinction compared to those of the ID data. Therefore, even when trained without any reliance on external auxiliary datasets, the detector will have a notable capability to distinguish ID data from OOD data. Now let's see the comparison results as shown in these tables. Firstly, we conduct experiments on the conventional OD detection benchmark using ImageNet as the ID dataset. To validate the effectiveness of our FA fairly, we mainly compare it with CLIP-based OD detection methods that do not use real outliers, such as previous post-hoc methods, zero-shot methods, and prompt learning methods. Our FA achieves state-of-the-art OD detection performance among other CLIP-based methods without sacrificing the ID classification capability of the model. Secondly, to fully substantiate the effectiveness of our FA, we leverage 3 additional cleaner and more challenging OD datasets, such as OpenImageO, NINCO, and ImageNetO. Notably, both our FAMCM and FAGL consistently outperform current SOTA methods. More details under the 1-shot and 4-shot settings are provided in the appendix. Then, considering factors like dataset variety, image resolution, and the number of classes, we also leverage 8 additional widely used datasets for few-shot setting as ID datasets for comparison. In particular, For the satellite ID dataset, FAMCM surpasses the best competing method LOCOOP by 16.09% in average OROC and 38.7% in average FPR95, underscoring its effectiveness and versatility even when the ID dataset is of low resolution. Finally, we conduct a series of sensitivity and ablation studies, as shown in these tables and figures. For sensitivity studies, overall with K ranging from 1 to 6, our method is stable and outperforms the best baseline. Especially as K increases, the average AUROC shows an upward trend and then tends to be stable, showing a bottleneck in capturing more comprehensive semantic representations of the ID classes. For ablation studies, we demonstrate the effectiveness of our FCE loss. Then, compared to random initialization, employing consistent manual initialization for both prompts enables the forced prompt to effectively learn more specific descriptions of the ID classes. Moreover, we also explore the influence of the shared learnable vector and the independent learnable vector for the forced prompts. We can observe that using the shared learnable vector performs well in the few-shot setting since the independent learnable vector for each class has more parameters and requires more training data. That's all. Thank you for listening.